9.4 is what we call comparison of series. There are two ways to compare these series. There's what we call the direct comparison test and the, I believe it's called integral comparison test. No, limit comparison test, sorry, limit comparison test. And it's exactly what you might think when you see the word comparison. We're going to take the series that we're looking at and we're going to compare it to another to see if we can figure out the original series based on that other. So here's what we know. A couple examples. This is a geometric series. It's a convergent geometric series. However, this one's not a geometric series, okay? But I might be able to use this to figure this out. This is a p-series. This one's not a p-series, but I might be able to use what I can easily identify as a convergent p-series. This froze. Okay, to determine whether or not this would be a convergent series, just based on its relationship to the original. So half the battle is going to be determining which series most closely resembles the one you're talking about and picking one you know how to do easily. So direct comparison test says this. You have two series. One of them is going to be bigger or possibly equal to the other. If this bigger one stops at a number, that's what it means, converges, then it's forcing the one that's smaller to converge as well. So if the top stops, it forces the smaller one to converge. On the other hand, if the smaller one diverges, if the smaller one goes on forever toward infinity, it pushes this one to also go toward infinity because it's bigger than the other. In other words, if you memorize this, then the second way is just the contrapositive. Okay? The opposite of this and the opposite of that. Changing the order, changing the sign. Alright, so here's what it looks like. Determine whether the series below is convergent or divergent. And here's what I see. It's not geometric. Geometric would be raised to the power of n. It's not p-series, but it looks like a p-series. That right there would be a p-series. So it's different, but it's similar. If the answer to both of these is no, then we're going to consider the direct comparison test. Here's how it works. I think it looks like 1 over n cubed. So what I'm going to do is I'm going to take 1 over n cubed and analyze it. If this was a series, excuse me, from n equals 1 to infinity, that 3 exponent, according to the p-series, is greater than 1, therefore convergent, again, according to the rules of the p-series. All right, what does this look like compared to that? Well, rule of thumb is if nothing else is different, then the larger the denominator, the smaller the fraction. Okay? The larger the denominator, I'm dividing by more things, makes my fraction overall smaller. So if I know that this is a convergent p-series, which means it's stopping at a particular sum, then it's forcing this one that's smaller than that to also be convergent. Therefore, the original series is convergent because of the direct comparison test. I directly compared them. That's this statement right here. That's a direct comparison. Best way to pick the series you're comparing to is basically look at the parent function of the original. So the parent function of this would be like taking the n and losing the 2. All right, what's 1 over n to the 1/2? Well, that's an exponent that's less than 1 but greater than 0. So this would be a divergent p-series. How do these compare? Larger denominator, smaller fraction. If this series is then
here's what it's saying. This is ever growing. It's greater than this. But does it tell us that the middle one stops? Or could this one also be growing toward infinity? One infinity could be larger than the other infinity, but this does not force this to cap. So this test is inconclusive. We can't use the direct comparison test for this example. So then what do? We come up with what's called a limit comparison test. And the limit comparison test says you take your two series, the one that's the original and the one you're comparing it to. If the limit of one to the other is a solid number, finite positive, then you know that either they both converge or they both diverge. So if I compared these two as a fraction comparison, and it came out to be a number, I don't care what kind of number, but a number that's finite and positive, then I would know that they were both divergent because the one was. All right, is that the next example? Yep, so we're going to look at that example again, except through the eyes of the limit comparison test. It doesn't matter which one you put on top. Just doesn't. Now, if I actually simplify this, I would multiply by the reciprocal of the denominator and I would end up with this statement. L'Hopital's rule is going to have to come into play because I have infinity over infinity. And after L'Hopital's rule, I get 1/2 n to the negative 1/2 over 1/2 n to the negative 1/2, which is 1. 1 is not any particular answer except a confirmation that these behave the same. So if the series I compared it to is divergent, which it is, then both are divergent because I used the limit comparison test. Okay? Give you a second to look at this one. If you stripped it down to its parent function and basically paid attention to just the variables, you have an n in the top, an n squared in the bottom, so we're going to compare this to 1 over n. Well, what do you know about 1 over n? I know that it's the harmonic series where p is equal to 1, so it's divergent, because remember, for a p series to be convergent, it has to be greater than 1. I'm not prepared to compare these directly in an interval, so what I'm going to do is just jump right to the limit comparison. I like the limit comparison better for that reason. It seems to work pretty much all the time, at least when comparison tests are to be used at all. In other words, I end up with this flipped, so n squared plus 1 over n times 1 over n. Okay. This simplifies to n squared plus 1 over n squared. L'Hopital's rule, well, first I have infinity over infinity, so after L'Hopital's rule, I end up with 2n over 2n. I have another 1. Since that's a finite positive number, then I can make the statement that both the original and the one I compared it to are divergent because the one I compared it to was divergent. Okay? So I'm going to say because of the limit comparison test. One more. Determine whether the series below is convergent. Again, go to your parent function. Strip everything down to just the leading terms, variables, and their exponents. My numerator would be n squared. My denominator, if the only thing I cared about was the leading term really stripped down to just the variable, would be n to the 5th. N squared over n to the 5th is 1 over n cubed. So I'm going to compare this to the series 1 over n cubed. It's a p series, p for the exponent. That's greater than 1, so I know it's convergent. If my limit comparison gives me a finite positive number, then I know that both of these are convergent because that one was convergent. So limit comparison test. I'm going to take 1 over n cubed and compare it to n squared minus 10 over 4n to the 5th plus n cubed. In other words, I'm going to flip around some stuff here, and I've got 4n to the 5th plus n cubed over n to the 5th minus 10n cubed. If you're not sure where that came from, I flipped this and then I multiplied the denominator by that. All right, numerator and denominator both become infinity, so I'm going to take L'Hopital's rule and apply it, and I get 20n to the 4th plus 3n squared over 5n to the 4th minus 30n squared. I'm going to pause because we can go through this a few times, but there was a rule we learned from Calc 1 that said if your exponent, leading term exponent, matches in the top and the bottom, then your limit is the ratio of the coefficients. So I already know, without having to go through several of these L'Hopital rules, that my limit is 4. It's the coefficient of 4 to 1. This is finite, and it's positive. So because I used a convergent sequence and I got this kind of an answer, then I know that both are convergent by means of the limit comparison test.